Okay. Good morning, everyone, and thank you for joining us for today's webinar on enhancing geospatial monitoring of natural hazards using IoT, geophysics, and remote sensing. We are very happy to have Dr. Maneesha V Ramesh, Director of the Amrita Center for Wireless Networks and Applications, and Dr. Sebastian Uhlemann, postdoctoral researcher from the Lawrence Berkeley National Laboratory at the University of California, Berkeley, US, and visiting professor at Amrita, with us today to give an informative and insightful presentation. The presentation will be followed by an interactive Q&A session. Before we start today's webinar, I now invite Dr. Maneesha to commence the presentation.
Good morning, everybody. Thank you for joining the webinar. We are very happy to have you all here to discuss about the different research activities between both the groups we're working on and how we are able to actually come up with an integrated approach for enhancing the geophysical monitoring. Just to give an introduction about the university, Amrita University is one of the youngest university recognized as the institution of eminence by the government of India. As of today, we are ranked as #1 private university by THE, the world ranking, and also with the QS, we are the #1 faculty. And very recently, the THE ranking for Asia level, we are among the top 10 universities in India. And we are very proud that within this short span, we are able to become the 8th best university in the country. What makes it different, Amrita University, is its vision and mission laid out by our Chancellor Sri Mata Amritantamayi Devi, where we focus on education for life, compassion-driven research, and global impact. We all know that education is needed for life and living, and we focus a lot on providing the understanding of the essential human values and imparting the culture of the heart to endure the values and the inner strength for the student and the faculty community, which helps them to deliver compassion-driven research where they are not only doing a mere work, but they are basically looking into how they can solve world's most pressing problems and culminating a research which has a large impact on the society. And at the same time, it's not that we want to stand silent. We actually bring in collaborations from different parts of the world so that we will get equipped to solve the global challenges. And this is one example where we are working for several years with Professor Sebastian for taking forward this collaboration in the geophysical monitoring. And Amrita, at a glance, as of today, we have 6 campuses with more than 20,000 students with 207 programs and spanning across 120 plus disciplines. We have campuses in Kerala, 2 campuses in Kerala, and one in 2 campuses in Tamil Nadu, 2 campuses in Bangalore, and new campuses are coming in Delhi and Andhra Pradesh actually. And very large focus on multiple disciplines that makes us stronger to come up with local solutions which are needed for the society, with the disciplines spanning from engineering, medicine, sciences, management, agriculture, etc. The strength of the institution is there are 5 strengths. I would like to say that the strongest one is naturally the interdisciplinary, which actually spans across from biotechnology to nanotechnology to engineering to medicine to cybersecurity to behavioral science to smart cities, social science, arts and humanities, etc., which actually gear the rest of the things like innovation. We are known of the best TBI in the country with more than 122 startups. We are one among the 6 TBI which has been equipped by Niti Aayog to actually bring up the incubation or the entrepreneurship in the country. We are very strong at international. We have more than 180 collaborations with more than 200 plus research collaborations, having the highest number of international faculty and the international programs with more than 5,000 plus exchanges happening all around and a lot of degree programs. As you see, different continents have very large number of collaborations. Highly focused on industry, we know that we have to work in hand with industry. More than 50 plus industry academia joint ventures with very recently we have got the Graham Bell Award for Mobile Health, Bulletproof Vest, which has actually helping the government to bring down the cost in a large scale. Building simulators which can actually train the machine shop employees in L&T and other industries by using haptic technologies and computer human simulations. All this is geared also towards India, our land, where we are looking into how we can bring in sustainable development in villages in several thematic areas like water, education, energy, skills, health, sanitation, disaster. More than 108 communities we and our students together are working, where students get the opportunity to work in these communities to work on real life problems. With this, I will hand over this presentation to Professor Sebastian.
Yeah, thank you very much for the introduction, Maneesha. This was great. What I'm going to do now is I will go and start focusing a little bit about what this webinar is about, so enhancing geospatial monitoring of natural hazards using IoT, geophysics, and remote sensing. So what are we going to talk about? Well, this webinar is about natural hazards. So one of the natural hazards is landslides, and I quickly introduce this. I will also talk a little bit about the research that we're doing here in Berkeley. And then Dr. Maneesha will come back and talk about wireless sensor networks and IoT. And then I will continue with geophysics and remote sensing. And at the end, we will show some of the opportunities that students and researchers, but also professionals have in this type of research. So landslides. This is a map of global landslide events. And you can see pretty strikingly that you have a lot of landslides in areas where you have a lot of steep topography. So on the Indian subcontinent, but all around the Himalayas, you have a lot of landslides in the Andes. But then also you have a lot of landslides actually in England, where you don't have that steep mountains, but you have a lot of clay and a lot of weak material. And the same is also true in the US. So landslides are very, very major and a very common natural hazard, actually. Just to come back to the US, in the US, I'm sitting on the West Coast, so in Berkeley. And around here, we actually have quite a lot of landslide hazards. And you can see this in these orange and red colors on the map, which basically show you that there's a high occurrence or high incidence rate of landslides. So landslides are really a problem all around the world. And in the US, every year, landslides cause more than $2 billion in damage and 25 to 50 deaths per year. And in comparison, the fatality rate is actually pretty small. And that's mainly because here landslides happen, for instance, along the West Coast, which is not that densely populated. So if you then go, for instance, towards Asia and Southeast Asia, you can see that there are a lot of landslides again. So the landslide frequency is shown here in kind of blue to red colors, where red colors mean that we have a lot of landslides. And these balls that you can see from white to purple, the size of these balls shows you how many fatalities you get. And clearly you see that here in these highly densely populated areas, landslides actually cause a lot of fatalities. So landslides, as I said, are a major natural hazard. They cause a lot of destruction, but also, unfortunately, a lot of deaths. One way of dealing with this risk is by kind of forecasting where we get landslides. And one way that's being done quite often is by using rainfall, where you just basically relate the amount of rainfall to where a landslide would occur. This is something that can be established reasonably easily, but it also depends quite a lot on your weather forecast and how well this relationship between rainfall and landslide actually holds. And in many cases, this is not the greatest estimator. So a lot of the research that we're doing here is actually focusing on basically trying to understand what's happening in the subsurface and using this as an estimate of when landslides happen. And that's kind of what we're trying to talk about today. So how can we use measurements of, for instance, the groundwater or the pressures that we have in the ground, how we can use them to predict landslides, and by doing so, actually help to save lives. So what are landslides? Just a very quick definition. Landslides are very, very simply the movement of a mass of rock, earth, or debris down a slope. So just what gravitation brings. So it brings down, as we can see in this picture here, just this slope that is just flowing down the slope and basically destroying this road here. And landslides, as I already mentioned, can be caused by several factors. One of them is earthquakes. So where you get strong earthquakes, the earth shakes quite heavily and then can cause landslides to occur. One of the probably most frequent causes is actually heavy and prolonged rainfall. So for instance, where we get monsoonal rainfall, or also here in the West Coast during winter, we get very strong atmospheric rivers where you get a lot of rainfall, and then you get a lot of landslides. And landslides occur both on natural and engineered slopes. And engineered slopes, one example is, for instance, levees. So the kind of earthen embankments that protect us from floods. And that's another kind of application that we're looking into, especially here in California, because levees are actually pretty vital to our nation. And that's true not only for the US, but for instance, also for the Netherlands, that basically wouldn't be there if it wouldn't be for the levees. So we have to find a way of also seeing how these engineered structures, how they perform under flooding events, under just heavy rainfall events, but also under earthquakes, but also just by seeing how they develop over time. Because the same as with your house, if you don't maintain it, it may break down at some point, and the same is actually true also for levees. So levees, especially, well, in California, but also all around the world, they are old and they are starting to fail. Here in California, we have 60% of levees actually at high risk, which amounts to more than 1,200 miles. So a lot of areas actually, at risk of flooding. One example we can see during Hurricane Katrina, where more than 50 levees actually failed around New Orleans, and we see the result of this in this photograph down here. The entire city got flooded, and we got more than 1,000 fatalities and actually also more than $70 billion of damage. And climate change, as we're experiencing right now, is actually worsening the problem, especially in these coastal areas that are highlighted now here. So if I go back and forth, we can see these coastal areas. This is where the sea level will rise and will put more problems onto these levees. So what are we doing, or how are we trying to deal with this? One of the approaches that we are developing here is using a combination of different data streams, so remote sensing, IoT, geophysics, and include them into hydrological and geomechanical modeling to basically try to predict where levees or where slopes will fail. And we're doing this because what we're trying to do is to provide early warning to the people that live close to these levees or slopes, so that they have time to actually get away from the potential threat. And what we are going to talk about today is not the entire kind of workflow that I'm showing here, that we're going from the data over a model to kind of our prediction. What we're focusing on today is just these two things. So we will talk about remote sensing, but also geophysical and environmental monitoring. And that's where Berkeley Lab has quite a lot of expertise. And that's just an example of what you could call intelligent infrastructure or adaptive infrastructure. So here in Berkeley, what we're working on is different things. One is emerging sensing and communication networks. So we're actually using unused communication fibers to estimate the properties of the subsurface, but just basically shining a light into these fibers and seeing what comes back. We're also using smart electricity meters to measure the impact of earthquakes. And by measuring this, we can actually then feed this into models, and we can estimate, for instance, how all the bridges that are in the Bay Area, how they behave under these earthquakes. And what we're starting to focus on now is actually these water retaining structures, so dams and levees, just because they are starting to pose a quite significant threat to the area here. And we're trying to incorporate new technology as well, like, for instance, emerging 5G technology. So one of the examples here, levees and the landslides, is very similar, especially the same problem that we are trying to address. So when a levee fails, what we have is that the slope basically slips or fails, and we have the water that then floods this area. And it's very similar to the process that we see in landslides. And the way we are trying to tackle this by using IoT, so we have measurements we have probes that measure temperature, groundwater level, but also deformation at certain locations. And then we're trying to integrate this data with geophysical data, because geophysical data usually helps us to provide spatial images of what is in the ground. And then all of this is connected, and we're using remote sensing, so small little drones, for instance, that can tell us about kind of more the wider spatial scales that we're looking at. So really what we're doing here at Berkeley Lab is we're trying to enable intelligent and adaptive infrastructure to provide resilient systems. So with this, I think I can give it over to Dr. Maneesha now.
So, Maneesha, you want me to talk about the center?
Yes, sir.
Okay. Good morning, everybody. This is Setu Rao. I'm a professor at the Center for Wireless Networks and Applications at Amrita. As Dr. Maneesha, mentioned at the beginning, Amrita has a lot of research centers, a lot of centers of excellence that are focused on different areas of research. One such research center at our Kollam Amritapuri campus is the Center for Wireless Networks and Applications. This center is headed by Dr. Maneesha. She's the head of the center. I'm a faculty at the same center. This center, like many other centers, has gotten many accolades. It's been recognized as a worldwide center of excellence for landslide disaster risk reduction by the World Landslide Forum. So it's a big recognition. So I will give you a brief idea of the educational and research activities that are going on at the center. On the academic front, we offer three master's programs. One in geoinformatics and earth observation. So as you can imagine, this seminar or webinar has a lot of relevance to this area. Geoinformatics and earth observation. We also have a program, master's program in biomedical instrumentation and signal processing. Biomedical instrumentation and signal processing. We work closely with our hospital and medical school at Kochi, the Amrita Institute of Medical Sciences. So there's a lot of research that happens, in those areas. And the third program that we have is known as the wireless networks and applications. So this kind of provides the glue for all our research in the areas of wireless communication in general, focusing specifically on applications of social relevance. I'll get into the projects a little later. So to kind of recap, we have three master's programs: geoinformatics and earth observation, biomedical instrumentation and signal processing, wireless networks and applications. We also have a PhD program. So we have nearly 30 PhD scholars working in the associated areas doing their research at our center. We have several international faculty at our center, both full-time faculty as well as adjunct faculty, visiting professors. Seb, for example, is a visiting faculty at our center. I myself, I've had international experience. I was in the US for 18 years, and then I joined Amrita 8 years ago. And there are many more such faculty at the center. So that gives you, overall international perspective when it comes to the academics and the research that goes on at the center. In terms of the labs that we have, we have more than 6 crores rupees worth of hardware and software that are there in our labs, set up in consultation with the industry and constantly being upgraded. Both the hardware and software get upgraded, so the labs are state of the art. I'll give you a brief idea of the projects. You probably already have an idea, you'll get more idea based on what Dr. Maneesha is going to present. So these projects are the ones on which our master's students and PhD students get to work. So they pick a problem which pertains to one of these projects and kind of go deep into that. So that is how their projects are done. So the projects have a direct practical relevance. Many of our projects are in collaboration with both Indian and international partners. They can be academic partners like the IITs in India, or the UCs, the UC Berkeley, UC Irvine, a lot of UCs, not only UCs, many educational institutions, both in the US, in Europe, other parts of the world. So we have both Indian and international partners, both academic as well as industry partners. We also work with industry partners. And a lot of these projects are funded by agencies like DST, MIT, that is the Ministry of Electronics and IT. DST is the Department of Science and Technology, then Ministry of Environmental Sciences, Ministry of HRD, the Department of Biotechnology. So a lot of these funding agencies in India, they fund our projects, and the collaborative projects are funded such that the Indian side is funded by the Indian agencies, and the international partners are funded by their own funding agencies. All our projects have a direct benefit to the society. So that is one of our key, considerations. Any project that we do, there is a huge humanitarian angle. The humanitarian aspect of the project is very important. Dr. Maneesha talked about our engagement with more than 108 villages in India. So, there is also a program called Live in Labs, where our students, along with students from other international institutions and the faculty, they get to go to these villages and try to first-hand study their problems, understand the problems, and then propose solutions. So this Live in Labs is a very popular program, internationally well known. Our projects tend to be interdisciplinary. Again, Dr. Maneesha talked about it. That is one of our key goals. Research is interdisciplinary, so projects are interdisciplinary, the teams are interdisciplinary, system level projects. So a complete system involving hardware and software, involving social engineering, all aspects are taken into account. A complete project is worked out and deployment oriented. So deployment is very important. As we can again see today, the landslide monitoring project has several deployments. You'll get to hear more about that. And the same thing with many other projects. Again, if you go to the website, you will get to know a lot more about our project. I don't want to spend too much time. I want to hand it off to Dr. Maneesha as soon as possible. So in our projects, we always ensure that there is a direct involvement of the stakeholders and the beneficiaries. So we get first-hand feedback from them, incorporate that feedback, and thereby make our projects more meaningful and more applicable to the real needs and the real demands of the people who actually need that solution. Finally, internships is a integral aspect of our master's programs. So it's a 2-year program, and in the second year, quite a lot of the students get to do their internships at the industry, and some of them even get to go abroad, to some of the international universities with which we collaborate. So of course there are also things like dual degrees and student exchanges with these international universities, which give you international exposure. And also when you work on your projects, because these projects are collaborative with international universities and education institutions, you get co-guidance from international faculty like Seb. There are many such people with whom you get to interact directly, and you get to work with them, thereby enhancing your horizons. And of course these internships very often, almost always, lead to placements. So when you go for an internship, if the company or the industry likes your work, they end up offering you a placement, and that's how a lot of placements happen. So again, to kind of recap, there are 3 programs, master's programs: Geoinformatics and Earth Observation, Biomedical Instrumentation and Signal Processing, Wireless Networks and Applications. If you have any questions, you can post your questions in the Q&A window. We will answer them later. You could also contact us later. So, and with that, I will hand off to Dr. Maneesha to continue with the webinar. Thank you.
Thank you, Professor Sethu. Thank you, everybody, and thank you, Seb. So I will move on to the topic, wireless sensor networks and IoT examples from India. I hope you are able to see the slide and the video. So as the title of the webinar says, we are looking into geohazard monitoring. Here I am taking 2 main examples. One is landslides and floods. India is always having the biggest trouble during the monsoon with these 2 major geohazards. And if we compare these two hazards, the landslides, it is especially occurring phenomena where it can start from a hill or a mountain to a bigger region. Floods will be much bigger region on a spatial where it can go to a catchment scale for several kilometers. In both the cases, they need temporal data to understand this phenomena. And in the temporal case, in the landslides, you will have rainfall-induced landslide and earthquake-induced landslides majorly. In the rainfall-induced landslide, it's predominant in monsoon period, whereas in the earthquake, there is an uncertainty in the event generation because it is connected to earthquake. So your data has to be accordingly collected. Whereas in the floods, for sure it is during monsoon period, but very rarely on an uncertain, even like a dam breakage also you can see that. So in both the cases, the data we need both historic real-time data, and at the same time to understand their phenomena and to move forward, we need the forecast also. And to do all these things and to communicate to the community, communication becomes very important part, and how do we communicate to the multiple levels is what we have to also look into it. At the same time, you can communicate, but how do they understand and how do they take action? So it needs a multi-stake engagement when the whole disaster management happened itself. And this phenomena has an annual recurrence, but at the same time, in the case of landslide, there is an uncertainty in location where the landslide is going to happen, even though we know landslide prone areas, whereas in floods, we majorly know what are the flood prone areas, and we can at least have a little more clarity on these are the areas or these are the floodplains which we need to look into. So as I was discussing on the temporal monitoring side, if I have to work on landslide monitoring, these are the key parameters on a temporal scale I have to monitor. I need to know the weather variability, which I may need to know hourly. What is the weather variability, a daily basis, and the last 7 to 30 days in a historic manner, and on a forecast of 1 to 7 days. All these different temporal scales, I need the data. I need to know what is the trigger factor, triggering parameters of landslides, which are multiple triggering parameters are there, and I need to understand the context at which this triggering happened. So all those things I need to have from data at milliseconds, days, and historic levels. With all this data, I need to understand what is the causal relationship between this data. Unless I have this data at these multiple temporal scales, I will not be able to bring out the causal relationship, which leads to the development of multi-thresholds and the dynamic decisions. Here also data becomes very important to understand the variability and the threshold variance with respect to the millisecond to hourly to the things, and these are developed based on the historic data in our hand and also with respect to the forecasted data. All this will lead to the multi-scale warning, which needs to be given in seconds or minutes or hours, and which will also need to use the daily forecast. So in the spatial monitoring, so we looked into the temporal. When it becomes the spatial monitoring, landslides can be on a site specific or a slope or a catchment or a regional or global. In the whole spatial measurement, based on that, the type of sensors needed, the area of coverage, everything will change from when you move from site to slope and slope to catchment. So site may be within a few kilometers, whereas slope can be maybe within 25 kilometers, or catchment goes much more, and the regional and global becomes very, very large region. So if you look into just trying to move away this. So if you look into in that case, for the multiple things from site to slope to catchment to regional to global, the different techniques we need, the different data frequency, the models, the thresholds, the decisions, the warning, what is the area of coverage, and the reliability is shown in this table. Where in the site we may be more or less working with more of physical sensor based systems on the slope, whereas in the catchment, since it covers larger area, you may not only physical sensors, you may need drone based remote sensing, crowdsourced data from the people, etc. And when it becomes to regional and global, it may become more of satellite based remote sensing or drone based plus crowdsourced. And at some positions, to validate that, you will have the geophysical sensors also. So if you see the data frequency on the site specific level, you may need highly frequent minute wise data, whereas in a catchment it is moderately, and when it comes global it becomes less frequent, like a daily scale. And the models also change as we move from site to slope to catchment to regional, because there are more dynamic parameters that need to be integrated, and based on those the thresholds will also change, because the thresholds at the site can be very location specific, and when it becomes to the slope, you may have to have the integration of different site specific thresholds, and leading to the finding out what is the catchment, what are the different slopes and how they behave, and then comes to the regional and global. So for the decision level, when you look into, when you want to cater to these multi levels, you may need from the single scale to the multi scale. And the warning itself has the multi-scale action, because when it is always it is a specific location within a slope, whereas when it comes to a slope it may be multiple mountains or hills. And when the catchment, you need to cover your communication to multiple states or districts, and in the regional to a multiple states, like a national scale. And when it comes to global, it becomes worldwide. But when you try to do this, the data, the availability of data, and the coercion and the fine-grained data which you will play around, your reliability of the warning will vary. That means the number of false alarms will vary. So you will have a higher reliability in the site specific compared to a very low reliability with respect to global, because when you say low reliability, that means you are not able to pinpoint the location. You know that in this region there is a higher probability of landslides, but I'm not able to pinpoint it is going to happen, the landslide in Munnar, in an Antonia colony town near this. So that is what I'm trying to say, that so the reliability level will vary. You will get a higher perspective of how the whole thing is changing on the spatial domain, but the specific location may be lacking, whereas on a site or slope, you will be able to get that. So it's up to the designer to decide what you want at what point of time. To the next slide. So in the whole geospatial monitoring, the major challenge which you will see is like, you have always trade-off while you want to do it. One is spatial wise, temporal you have trade-off, because if I want to, as I already discussed, you may have to decide whether you want to have a large area based monitoring or location based monitoring or multi-parameter wise monitoring, because when it becomes more of temporal and very location specific, you may need multi-parameter, whereas in the large area you may not need that much. At the same time, another one will be the reliability wise cost. So based on, if you want more reliability, your cost will naturally increase, because you may need large scale deployment and very sensor based systems with heterogeneity, simulations, experiments, etc. will come in. At the same time, the other major trade-off is between heterogeneous sensing wise resource constraints. You may have to bring in multiple domain perspectives and multiple types of sensing systems to have a comprehensive understanding of how this phenomena is varying. But when you want to do that, there will be a constraint on how much data you can collect and how much, when you want to collect, transmit, process, etc. It will bring in the constraints with respect to energy, memory, computation, etc. And this is leading to also another trade-off, which is do you want geospatial monitoring, or how, when you try to do the geospatial monitoring for a large scale area, how does it affect in developing dynamic thresholds, because the climate is varying, the triggering parameters are varying, the inherent parameters of the Earth's system is varying. So you will have to deal with heterogeneous data. That means separate multi-domain thresholds needs to be developed, which needs to be integrated. So it becomes more and more complex when the spatial thing will increase. And at the same time, you need to have historic and real-time data to get into the even identifying the data. So do we have those data? Do we have the forecast for each of these different parameters? And another major thing becomes local decisions while global decision. do we have the coverage of the sensing system to take whether it is local or global? So once the coverage is increased, naturally the reliability has an effect. Then the connectivity becomes a bigger problem, because most of these disasters happen in very harsh environments and the harsh climatic conditions, and your connectivity between the sensor nodes becomes very bad during those times. And you need to decide between the fine and coarse-grained data availability to have these multi-scale decisions. So to enhance the geospatial monitoring, you need to bring in heterogeneous sensing techniques, resource-aware service management, learning temporal interrelationship, learning spatial relationship, dynamic decision models, and multi-scale warning. So in the heterogeneous sensing, you may have to bring in remote sensing based, physical sensor based, participatory sensing based. These are some of the topics which we will talk in this webinar. To make it resource aware, you have to look into energy efficiency and the real time, whether the system you need as real time or a delay tolerant or a fault tolerant method. You need to have time series and machine learning methodologies to understand the temporal relationship. You also have to bring in the geospatial analytics, machine learning, big data analytics, etc. to understand the spatial interrelationship, and to get dynamic from the static to the dynamic decision models, machine learning and AI technologies and multi-scale warning will need integration of site to global scale decision models. So any disaster you take, whether it is landslide, flood, avalanche, forest fires, earthquake, etc. At the end of the day, all of these have these different scales, and you need to have data of different types too. So in this scenario, Amrita has actually brought in Amrita has brought in an IoT platform which basically has the edge layer, fog layer, and the cloud layer. You can see the ubiquitous edge layer for fog layer and the cloud platform, and you have edge nodes in the sites where it will actually get the data from either physical sensors or crowdsourcing or etc. And all this has to be in the fog layer, has to have its own processing with respect to the storage, the physical sensors, looking at into how the data has to be handled, and the location identification and the command and control. Based on all those data, we will have further data from remote sensing and meteorological databases to do the cloud computing and then derive the decision models, forecasting and warning messages. As you all know, India, the landslide scenario is majorly affecting the Himalayan region and Western Ghats. Based on the color, you can see the red is very high and yellow is the low hazard areas. And all these four areas, the northeastern Himalaya, northwestern Himalaya, Western Ghats, and eastern Ghats, they regularly go through the landslide problem. And to achieve a full-fledged landslide disaster reduction, we need to have a multi-pronged approach with transdisciplinary capabilities and community empowerment to multi-scale needs. So in this whole work, we have actually looked into the vulnerability mapping of landslide prone areas, geotechnical analysis, real-time monitoring, multi-scale decision models, and integrating with community by resilience programs and social media. We have deployed this system in Western Ghats and Himalayas for real-time monitoring of landslide and early warning. More than 400 sensors has been deployed in this area to actually monitor in real time multiple parameters that are causing the trigger of landslides. You can see people are living in all these regions, and it's highly necessary for us to actually save their life. Over the years, we started in 2006 and we have moved forward with a lot of projects, with the different project fundings from national and international, and becoming World Center of Excellence in 2017, and US patent has been granted in 2014 for these projects. So if you see this figure, we have deployment in the Sikkim area. We also have deployment in Kerala. In both of these places, we have deployed the sensors. If you see, this one is the deep earth probe, which has multiple sensors deployed in multiple layers, which basically says in each of the point. So I have a moisture sensor, which will tell me the moisture at that point. I have a geophone, which will give me an area-wise seismic, how the seismic signals are coming in. I have tilt meter, which will give me how much tilt is happening in the soil, and the rain gauge, which will give me the rain, and the strain gauge, which will tell me the strain is produced in those deep earth probes when the land start moving, and I have pore pressure sensors which will give me the pore. So these are integrated through a communication system with the heterogeneous wireless, and then the data is collected and warnings are issued. In all those things, we have looked into how the multiple features can be integrated, multi-layered approach, dynamic learning, artificial intelligence, dynamic decisions, and integrated warning as an automatic system. So here you can see there is cloud, fog, and edge. You have sensing layer, which actually brings in together the multiple heterogeneous and homogeneous sensors, data acquisition and communication layer, network layer, knowledge discovery, and knowledge dissemination. This becomes very important for whatever data you are collecting. If you don't have the last three layers, it is difficult for us to issue an early warning, where we need to look into how the landslide risk, and we also has to look into how we will bring in the multi-threshold development and how to integrate with the slope stability models and bring in the adaptive learning. So we will be able to provide the risk alert to the people. And these are the heterogeneous sensors, which I have already talked to you about, this multiple sensing at multiple layers, which all this data are connected to the edge node, which is sitting here, which has the different capability to manage this data. And as you know that since it has multiple sensors connected, the energy consumed by them is very high. So we look into the context, and then based on that, we will do the dynamic sensor activation, multi-level, multi-sensor prioritization, and context-based data collection, so that energy can be saved, so that the complete system can have a lifetime much higher than if you don't have this context-aware energy management. So if you see that at the moment you have the context-aware management, it has its power is actually going for more than a month. You are able to work without replacing the whole system. As I already said that we have this 24/7 operational wireless sensor networks with multiple wireless looking into fault tolerance, integrated with ZigBee, Wi-Fi, long range Wi-Fi, etc., satellite network, and also cellular network to get this site to slope to catchment to the regional level of monitoring landslides. All this data comes to the real-time visualization, where people from anywhere can be shown who have the access to that network, and multiple sensor data can be seen in multiple windows, and each of those can be further looked into and dive deeper into it. But what makes it different is the decision support system, which provides a continuous enhancement. And why are we able to do? Because we have a decade-long data from the sites where we have deployed in the Western Ghats in Munnar and also in Chantmari in Sikkim. And this decade-long historic data plus the real-time data analysis together is fed for the adaptive learning, and which is helping us to have the forecasting. So we basically bring in the meteorological, geological, hydrological, and vibrational data, and we do the spatio-temporal data mining and machine learning models and threshold models for the heterogeneous data. In this process, we were able to actually develop the rainfall intensity threshold for Chantmari, which is the Sikkim area, where we have built for the regional rainfall threshold for the whole of Sikkim, and also we were able to build the local rainfall threshold, which is for the site-specific Gangtok area specific data, where you can see that all the places where landslides happened is the red one, and those are above the threshold line which we have set up. And this particular model has been implemented into our network, and we are using it. And over the years, if you see the cumulative rainfall are increasing over the years, and you can see the landslides which have happened in Munnar during this period. So if you see this one, when you see between two heterogeneous sensors, here there is the rainfall data, and here there is the pore pressure data. You have over the years from 2011 to 2017, these are the rainfall you are seeing, and then you are seeing the pore pressure. If you see that for a long period, pore pressure is not changing, and at some point suddenly pore pressure goes high, and that's when you see the event happening. So that means it's very important how you collect the data, how you actually do the processing, so that you don't miss the real-time event. That is why you need heterogeneous sensing. You also have to be context aware in doing this. So in this regard, to don't miss the data, and also to have forecast early, so that we can save life. See, if we tell 5 minutes before if a landslide is happening, it's difficult for us to move away the people from the slope and then save them. So how do I get more lead time so that I can forecast it ahead, and so that the government get an opportunity to move to take the people away from this region? Here we have actually used the machine learning and artificial intelligence concept to understand from our historic data. If you see, the green color is the historic data of pore pressure data, and we used the machine learning techniques to understand what is the adaptive learning which we can do, and based on that we are able to forecast. So if you see that after some time, if you see that this is the actual pore pressure data, so and this is our adaptive data. So it almost goes at the same line, where we are able to use this data to forecast and tell the people, saying that okay, it looks like the factor of safety of the whole mountain is going down, please move away from this place. Not only this, we also have landslide laboratory setups which actually looks into rainfall induced landslides with respect to the hydrological manner and the geological manner, and also the movement scale laboratory setup which looks into the inclinometer strain gauge based methodologies. So both of these laboratories have the capability to simulate rainfall, and at the same time also have seepage simulators, so that we can arrange the various infiltration rates with multiple soil composition and come up with different thresholds and use that for validating what we see in the field. With all these things, we come up with the 4-level warning system, taking each of the data and using at different levels, and based on that we are issuing the automatic warning. From the first level, you are only looking at global rainfall thresholds, where the data is coming only to the researchers, the alert. Whereas second and third and fourth, if you see, it goes from government to media to public, where each of the level you are increasing your capability of data analytics and data science approaches, which helps us to forecast an early warning. And we validate all this with respect to field data, landslide, laboratory and slope stability models before we issue the warning. In the recent 2018 and 19, Kerala has experienced large landslides, and it became a multi-hazard with extreme rain of 42% departure from the normal, and flood of 14% and landslide more than 200 plus, with the dam opening of 36. All districts of Kerala on red alert, death toll of 450 plus, and more than 1 lakh has been displaced. You can see how each of these places where the whole Kerala was under the flood. We are able to use our landslide system in Munnar to use the decision models and issue 3 warnings, one in 12th July, another in 15th July and 9th July, and people were evacuated and saved. And you see that this is a visualization of our system, where the yellow color shows that it is getting into the alert level, where the warning level, and as the color changes, its alert is changing. So we were able to alert very specifically on a regional scale, saying that this is what it is going to happen in the regional scale. And we were able to also say on a location specific case, where we, based on our sensor, in this particular location it will not happen, whereas in a regional there is a higher chance of landslides happening. So it has helped us to enhance the reliability of landslide warning, because normally people will issue just the rainfall based threshold warnings, which is more of a regional, and so people will wait and then they will see there is no landslides happening in their location, and they get into the confusion thinking that we are giving false alarm. It's not that, because it's a regional scale, so the reliability does not come to the point. So when you have integrated with the site, it will give that reliability, where you are able to confirm and tell in that place whether it will happen or not. And not only using the IoT sensor, we also used in Kerala floods the crowdsourcing system, where we have developed, where we used it for actually providing the information about the flood system and the thing, and at the same time we use this system for on a geospatial manner to monitor where the victims are, what are the help needs, how do you rescue them, how do you rehabilitate them. And a set of students from the university has run a call center 24 hours for all these weeks, whose data also has got into this, which helped both the administration and the volunteers to have an effective relief and rescue operation. So what does it mean? I am only talking very few of them, but what does it mean? It clearly tells us we need an adaptive and integrated community disaster resilience, where it needs preparedness, response, mitigation. So we used the crowdsourced mobile app and social media based awareness program and IoT system monitoring for preparedness, and for response we used the Amrita mobile app, the 24/7 call center and in-field volunteering. And for mitigation, we use the early warning system, the risk communication using mobile application early warning. So thus, we were able to bring in the adaptive integrated disaster resilience, where we brought in the solutions adaptable to dynamic risk variation and integration of technical, social and managerial solution. But if you see that in each of these things, it was highly necessary to have an integration of multidisciplinary team to work together in building this bigger scale, large scale solutions. So in the whole geospatial monitoring, it required the integration of GIS techniques, geotechnical monitoring, earth system science, machine learning, remote sensing, Internet of Things, big data analytics and modeling. So if you see that, this is what we actually envision as a wholesome program which provides the opportunity to build large scale systems which can save people, and that's where the MTech in geoinformatics and earth observation help you to learn all these pieces and able to use it for different types of natural hazards, different types of monitoring systems. So with this, if the whole system, if you see, it has all the capabilities from monitoring in site characteristics to laboratories to modeling to sensor system to algorithms to communication system to software system, dynamic learning and multi-level warning system, which will basically go for a geospatial monitoring on a multi-scale approach. So if you see that, as I earlier said, our system is able to have look into this multiple scales, which is basically reflecting into as edge nodes and edge layer and fork nodes, fork layer, cloud, etc. to achieve landslide warning and at the same time building resilience in the community. So these are the different technological and scientific advancements we could bringing in low-cost systems, bring in multi-parameter monitoring, modular, scalable, lightweight middleware, sustainable hardware, machine learning based multi-parameter, slope stability, context-aware techniques. These all has helped us to get the award for the World Center of Excellence on Landslide Disaster Reduction by the International Program on Landslides. With this, I pass this presentation to Professor Sebastian. I hope everybody, I hope I was not too fast. Because of the time constraint, I was running fast.
I think it's fine. Okay. Should I continue? Yeah. Maneesha, could you turn off your? Can you mute, please? Because I think I can hear myself. Okay, thank you. So yeah, as Maneesha already said, there are lots of different sensors that you can deploy and that you can use to predict and monitor landslides. What she hasn't touched on, or well, what she mentioned is also geophysical sensing and geophysical monitoring. And that's something that is kind of my expertise. So I did my PhD in geophysical monitoring of landslides. And so in the next 10 minutes or so, I will talk about this.
You have to share the presentation.
Oh, sorry. Yeah. That's a good point. So yeah, you should see it now. Good. So let's continue with this. So what I'm going to talk about now is a landslide in England, actually, which is very similar to the landslide in Munnar. Well, similar in a way that it is a landslide observatory. This landslide, in contrast to the one in Munnar, is actually not impacting on any village or any people. So this really is just a research site. But as you can see in this digital elevation model, there's a lot of deformation happening along this landslide. So you can clearly see that this slope is moving and deforming, and we can actually see this pretty nicely from year to year, as these kind of fingers that you can see here and here, they're moving by about 1 to 3 meters every year. So while we are studying it, we can actually see how this landslide is evolving, and we can also then study really which processes are causing this landslide. So the landslide, as I said, is in England. It is in a rock that is very weak. It is a clay that has very weak properties and fails very easily. So in comparison to Munnar or to the Himalayas, where you get landslides in very steep slopes, this slope only has a slope angle of 12 degrees, and so it's pretty flat, but it's still failing, which is quite surprising. But this basically shows you that it doesn't necessarily need to be a steep slope to have problems. it can also be, as in this case, quite shallow and it can still fail. The landslide itself is this kind of mudstone that is failing and it's sliding over a sandstone formation. And similar to what we saw already for Munau, or what Dr. Maneesha introduced, also here we have a lot of different sensors that are actually measuring the deformation of this landslide, but also measuring actually its hydraulic properties. So kind of the groundwater distribution in a landslide, but also how this distribution changes and how water gets into it and how water actually comes out again, and how this then relates to the activity of this landslide. So what we have at this site are a network of GPS stations. So these are measuring basically how the landslide is deforming at certain locations. There are also what we call tilt meters that are just measuring how the landslide is deforming at different locations. So here and here. Then what we are mostly interested in is actually the hydraulic properties. So we're measuring groundwater table variations, but also changes in soil moisture using a wireless sensor network. And then what is outlined here in red, this is a grid that is measuring the electrical resistivity of the subsurface. And we'll come to this in a second and explain a little more what this actually means. So this is just the cross section of the landslide. As I said again, it's a mudstone, so a lot of clay that is basically just flowing on top of this sandstone formation here and causing this landslide. As I also already mentioned, this landslide forms a test bed to develop novel monitoring technology. For instance, the University of Loughborough developed a low-cost landslide warning system that basically just measures the deformation of a pipe. And that's something that is now applied in a lot of countries worldwide, but it was developed actually at this site. But to really do this, what we have to do is we have to really understand what the landslide is and how it works. So this was kind of what we've been working on in the past. So we tried to really understand what is actually causing the landslide, not so much predicting how it's going to behave in the future. As Dr. Maneesha already mentioned here, we were really interested in understanding what is causing a landslide, so what are causing the deformations. So one of the things we used is basically seismic waves, and what I'm showing here is just an example of an earthquake, because basically what we were trying to do is something similar to what happens during an earthquake. So if we have an earthquake, so here what we get is we have different waves that are basically traveling through the subsurface after this earthquake happened. The fastest waves are these P waves, so they're pressure waves, and then the second fastest are usually what we call S waves, so they're shear waves. And okay, this is an earthquake, but we can also do a very similar approach by just hammering on the ground. Every time we hammer on the ground, waves will pass through the subsurface, and we can record when they arrive at different locations on the surface. And from this time, so what we can actually do is we can estimate the velocities in the subsurface. And these velocities are actually related to the density, for instance, and other parameters, and other elastic parameters that are actually quite important for landslides and how they behave. So that's something that we actually tried at this landslide in England. And the results of this we can see here. So what we did is, as I said, we just used the hammer and we hit the metal plate. You can see this here. And then we recorded how these waves that we are trying to trigger here, how they penetrated through the subsurface. And then what we can derive from this are areas where the waves travel very quickly, shown in red here, and areas where the waves travel pretty slowly, which is shown in blue here. We can then derive certain aspects. So in this case, for instance, we have these areas here, so high velocities there and here, and these are related to the groundwater table at this site. And already by having this information, that's some input then we can put into hydro and geomechanical models that we can then use to actually predict how the landslide is moving, but also we can use these models to actually further try and improve our understanding what the processes are that are causing these landslides. There are different things that we can do. We can also have a look at some of the elastic properties, and in this case, it's what we call the Poisson's ratio, and just very, very easily or very, very simplified, if the Poisson's ratio is low, and we usually have some dry material and Poisson's ratio is high, we get some wet material. And suddenly what we can see in the ground with these geophysical techniques is where we have wet material, so everything that's blue here, and where we have dry material, everything that's red here. And this again helps us to understand how these landslides are behaving and when we can expect them to move. But also, it can actually help us to design measures to stabilize this landslide. Then another technique that we're using, or that we used here, is electrical resistivity tomography. And what we're measuring there is the electrical resistivity of soils. And this electrical resistivity is just defined by mainly two things: by the electrolytic conduction, which is a function of the saturation. So if we have, like here, no water in our soil, the resistivity is very high. Then if we get some water into it, we're lowering the resistivity, and the more water we have, the lower the resistivity becomes. But also it will change on the pore fluid conductivity, so whether we have fresh water in here or salt water in there. And then it also changes on the temperature, but it's not that important here. One aspect that's also very important for the electrical resistivity is whether we have only sand or whether we have some clay particles in there as well. Because the more clay and the more water we have, the smaller the resistivity becomes. So clearly for landslides, this has a very high importance, because quite often landslides are caused by either water, so where we have high pore pressures, as Dr. Maneesha already mentioned, or we have clay, which is a very weak material. And both are sensitive to, or resistivity is sensitive to both of them. So clearly resistivity is actually one of the prime techniques or prime geophysical techniques to image and monitor landslides. And so that's something that we've done back there in England. So here you see just a 3D model that we can derive from our measurements, and we can very easily see the distribution and the shape of where this mudstone is. And then, so that's shown in blue here. And underneath that, we have our sandstone formation. And then at the bottom here, down at the lowermost bit, we can actually see where the groundwater table sits. So that's very interesting. And then what we can do is, if we take actually samples from the site and take them back to the lab and analyze the electrical resistivity with regards to the water content that we have, we can develop these relationships. And if we have those, we can actually start to estimate what the moisture content in this 3D volume is. And then we see that we have areas where we have very high moisture content, so a lot of water in the ground, and we have areas where we have very little moisture in the ground. So clearly, this already then gives us another idea of what we could potentially do to stabilize these landslides. So here I just want to show a video that that shows you some of the data that we acquired over a period of, I think, 2 to 3 years. So again, we see where this volume sits. So we have the blue colors, which show this low resistivity, so a lot of water, a lot of clay, and underneath these warm colors, they show sandstone, basically. So the stuff that's actually pretty stable at site. And then what we're going to look at is just changes in this problem. And what we can see now is to sudden see that suddenly we get a lot more. This is because 2012 in England was a very warm year, and it actually caused landslides to move after 4 years of movement. So this was pretty exciting because we were monitoring since 2008 and nothing happened, and suddenly in 2012 the landslides stopped moving, and it actually hasn't stopped since then. So let me just load this again. Okay. So if I just continue, so what we can see here now is just a few features that you can extract from these 3D models. One of them is preferential flow. What was interesting is that in 2008, basically, this side of the landslide failed. But then in 2012, we had a lot of movement on the eastern side. This side remained pretty stable. As I mentioned before, sometimes these geophysical data can actually tell you to stabilize the slope. In this case, the slope over here actually shows itself to stabilize itself. So in this case, we got a lot of cracks and fissures on the surface that actually help to divert water from the surface into deeper layers. And by doing that, it reduced some pore pressures that we had in this area that actually helped to stabilize the slope. So in this event, this remained stable and this site failed. So clearly, if we have this information, then we can also then decide future, for instance, remediation measures. So rather than, for instance, putting in a retaining wall at this site, potentially we would put in some drainage to remove the water that is basically accumulating here and then causing a landslide. And then the other thing we see, as I already mentioned, is these kind of drainage patterns that we clearly observe every summer. And that's important because it actually helps us to estimate hydraulic properties that we can then use to model this landslide. And similarly to what Dr. Maneesha already showed on forecasting and kind of prediction what's happening, we can also use some of these data to do the same. So what I show here on the top is just the resistivity that we extracted from the model. And we can see that over the first few years, the moisture content remained pretty low. But then in 2012, when the slope reactivated, it exceeded 48% actually. So it exceeded 50% by its maximum. And if we combine this with the measurements we have from site, where we see pretty clearly when the slope started to move, we can come up with a threshold. And in this case, we obtain a threshold of 48% moisture content that actually causes the landslide. And if I would now extend this plot and bring it up to the present, every time we exceed these 48%, we would see that we get these kind of events again. And they actually happen now every year. So every year we exceed 48%, and then the landslide starts moving. So clearly geophysics can be used to, or some of the data that we can gain from geophysics can also be used to forecast or predict landslide events. So this is just some data from the site that Dr. Maneesha already introduced. So that's the Muna landslide in the Western Ghats. And what we see here is some data that we got from UAV imagery. So if I just start or go back to the beginning, so you can see this is just a point cloud that comes from some drone images that helped us to define the digital elevation model. And then we see the resistivity distribution underneath. And here the color scale is slightly different. So here yellow colors are very high resistivities and blue colors are very low resistivities. And again, we can see that there are two different features. So we have something low resistive and something very resistive. And in this case, there was this landslide here. And we can see that what failed is basically this resistive material up here. And then over the time of the year, at this site, we're also acquiring resistivity monitoring data. And this shows you the effect of the monsoon in 2019. And you can pretty easily see how the monsoon is first infiltrating through the subsurface, filling up the top layer with a lot of moisture. But then if I go back a little bit, we also see that these last rainfall events actually led to a rise in the groundwater table. And we see a lot of changes also in deeper parts of the layer. So this is just everything I want to talk quickly about geophysics. And if you're interested more, part of this work is also covered in some of the MTech courses that are offered within the modules at Amrita University. So just to kind of go one step further. So what we've seen so far is a lot of local measurements. So if we look at the IoT and wireless sensor networks, there we usually focus, or we measure basically one value at one location, but then we use multiple locations and multiple measurements to upscale what we're measuring. The same is true for geophysics. We can measure this volume that I showed you. So this already gives you an idea of what's happening in this volume. The problem you have, though, is that this is pretty much local information. So we need some technique to actually upscale this to kind of the wider area. And what is used quite often is remote sensing, because that's something that can actually help us to kind of use our local knowledge. So use the understanding that we derive from these local measurements, and then extrapolate it to the regional scale. And I just want to kind of quickly summarize this here. So we've seen all of this. So we've seen IoT, we've seen geophysical sensing, and we've seen so far how we can use all this to help in providing early warning for landslides. So what we can then use to upscale this is really these either satellite products, or we can even use drones. And what we can do, or what we can derive from this is what we just saw in the case of Munar. We can get topography, but also if we repeat these measurements, we can actually get deformation rates. And with kind of latest developments, we even can get regional estimates of soil moisture in the ground, which is one of the defining factors on whether or not we get a landslide. So just to summarize this a little bit, in terms of just digital elevation models. So as I said, we can use UAVs, but we can also use satellites, and we can actually also use airborne devices. So here in this case, we have a plane that is flying over an area and is obtaining topographic information by basically shooting a laser pulse down to the ground and measuring the return of this laser pulse. And by doing so, it can actually get pretty accurate topographic information in the order of a centimeter or so. And we can get this at 0.5 meter resolution or even finer than that, depending on how high we fly, but also which system you use and so on. But we can get very detailed and very accurate topographic information that we can then use to identify landslides. So here it's pretty easy. You can see these very characteristic shapes. So this kind of half circle, and then you can see all the deformation that is basically downslope from this. But sometimes not that obvious, and sometimes it depends a little bit on how you process the data. But basically, with having this kind of detailed topography information, you can really be able to start to analyze a landscape and try to define where you have landslides. And also in this case, we see probably some paleo landslides here and there, and you can really start to understand where you had landslides, but also when you combine this then with your local knowledge, you can try to understand why these landslides are there. Then another application is, as I mentioned, deformation monitoring. And what is used quite often for this is what we call INSAR, which is based on a radar technique. And basically what it's doing is it's shooting down a radar pulse from a satellite to the ground. And it's basically measuring the phase that comes back. And by repeating these surveys and seeing how this phase changes, you can resolve very, very small changes in height, basically. So this measurement gives you a change in the elevation, which again can be used to map your landslide deformation, but it also can actually give you information about when a landslide failed if you don't have direct observations, but also how much it failed, so how much volume failed and so on. So that's a pretty good technique. The drawback of it, though, is that it depends on satellites which cover the same point on the Earth's surface maybe once a week or once every 2 weeks. So clearly there's a problem in getting the temporal resolution that you really need to monitor some of the really fast-moving landslides. And one of the drawbacks is also that here you're looking at ongoing deformation, which is already a measure of active failure. And usually what we try to do is we're trying to give warning before this active failure happens. But nevertheless, it's a very powerful technique that you can use as shown here to show, for instance, monthly displacements of a landslide in China. And here you can see just the amplitude, which is only 30 millimeters, so only 3 centimeters. But so clearly this has a very high resolution. And then one of the latest developments is a product from NASA, which is soil moisture active passive, so SMAP, which gives you an estimate of the shallow soil moisture. And that's very important because sometimes, depending on what the shallow soil moisture is, in case of a rainfall event, it could happen that you only get runoff, so nothing goes into the ground, which could be good or could be bad. Or if the soil is already wet, then a lot of moisture can go into the ground, which again can sometimes be good and sometimes be bad. But if you have this information and you know what the conditions are, then you can much better assess what the effect of different rainfall events on slope stability may be. But as with the other methods, so with INSAW, the problem here is again that you have repeat rates of 8 days or more. And so what's next? Really, what we're doing is developing algorithms to automatically feed there's different data streams, so the data from IoT, from geophysics, from remote sensing, to feed them all together into hydrological and geomechanical models. So this, as Dr. Maneesha already introduced, needs then some machine learning and deep learning, but also actually needs to develop these advanced hydrological and geomechanical models that can address 3D problems. And what we're trying to do with this is really to provide improved accuracy of landslide susceptibility and early warning. I think for the future opportunities, I just give back to Dr. Maneesha, and yeah, thank you very much for giving me the opportunity to present the work on geophysical and remote sensing that we're working on.
Are you able to see me, the slides from my side?
Yeah.
So thank you, Seb, for the detailed presentation. So with all these things, we would like to say that Amrita is working hard with all the international partners and collaborators in providing the future opportunities for the students. So there is highly interdisciplinary research direction is there in the university, where we work together with geotechnical engineering, geology, geophysics and electrical engineering, remote sensing and hydrology, data science and big data. Very strong international collaboration and open and collaborative science, and looking into you get the opportunity to work with international collaborators, go to these universities or the industries to work with them, earn either double masters or double PhDs. And it's a very timely research you are getting, very down to the needs of the people. So, and also you all know that this knowledge is very important for the upcoming smart city infrastructures and also the climate change which we are going through this. With all this as the intention, we have developed this MTech in Geoinformatics and Earth Observation, which provides a deeper understanding of these issues and provide comprehensive solutions through multidisciplinary curriculum. So we try to bring in interdisciplinary aspects with scientific, technical and social science, emerging technologies, which is pursuing cutting edge research in earth science, geoinformatics and climate change, and career opportunities in the field of GIS, remote sensing, big data, machine learning, climate change, smart city planning, disaster management, etc. And our collaborators are, we work very closely with British Geological Survey of India, British Geological Survey, ISRO, University of Trento, Italy, with the Politecnico di Milano, University of Buffalo, Ministry of Earth Science, King's College London. We have large project with King's College London and Newcastle University, BGS and UK Met Office on looking into landslide slope monitoring aspects in both local and global scenarios. We have faculty members from different places like Qualcomm, from NTNU, UTS, BGS, etc., who has their degrees coming from their international experience are from these places. That means they bring in that value to you. As I earlier said, this university is very committed to the society. We have more than 108 communities where we are working on the 17 sustainable development goals. We recently has launched a PhD in sustainable development with a fully funded PhD program. And it provides you hands-on experience in rural communities and help them to attain a sustainable future. So one of the major thing is like the whole fellowship is there. You also have the funding for deploying your solutions, and at the same time you have the opportunity to get it as a double PhD. So where we are working with our partners in getting you a PhD from Amrita and also a PhD from either Politecnico di Milano or VU Amsterdam or or from TU Delft or University of Buffalo, etc., based on your area. So you will always have a co-advisor from the international phenomena, and then you move forward. And as I said that there are 100 plus the E4 Life fellowships for this program, and we focus on education and gender equality, health and hygiene, waste management, infrastructure, energy and environment, agriculture, risk management, livelihood and skill development, water and sanitation. Best part is the students who join for master's program at Amrita get the opportunity to go for an integrated PhD, where their master's thesis itself get extended towards the PhD program, so that you will be able to finish your PhD much easier, and at the same time have a collaborative partner internationally, which will help you to get a double degree from them also. We also have MTech in wireless networks and applications, where our focus is on IoT networks, AI and machine learning. And at the same time, we look into the wireless communication aspects, the antenna design, the wireless networking aspects, working with, the 5G networks, working with also with software defined radios. We are also working with the IoT systems with edge, fog and cloud computing with big data analytics. We have dual degree programs with VU Amsterdam, University of New Mexico, etc. And our students have been to different places for doing their master's thesis, including Colorado State University, VU Amsterdam, ETH Zurich, University of Toronto, etc. And lot of international collaborations, and very unique opportunity to work with a highly talented and experienced research teams at Amrita and also internationally. Very good collaboration with industries. Another major program which we have is the MTech in biomedical instrumentation and signal processing, where it looks into both the IoT aspects, the biomedical aspects, and the uniqueness is Amrita is able to bring in the expertise from the Amrita School of Medicine, the School of Biotechnology, and also the Center for Nanoscience, along with the wireless networks and applications. We are able to actually bring in all of their capabilities, and there will be faculty from these multiple schools who will be teaching you to make you highly interdisciplinary and useful for the whole industry itself. And we have also collaborators and industry partners in the whole thing, where whatever you are developing becomes products, and we will talk forward as a incubator in our own TBI itself. So this is another major thing where we have highly experienced, and where our products are coming out, and that way you are able to work in multiple scales from whichever areas which you are coming in. I think with this we have covered all our webinar topics and the discussions. We are now open for the question and answer session.
Okay, thank you, Dr. Maneesha and Dr. Sebastian. We will now move on to the Q&A portion of the session. We have quite a few questions, actually. So I'll just scroll here to the first question. Okay, the first question is from Nirmita. The northeastern part of India has a high seismicity as per the data in recent years. That actually makes the region highly unstable. Therefore, what measures do we need to take before construction in these regions are made, and what might be the implications? Sorry.
Yeah, I think I already tried to answer this a little bit. Actually, so seismicity is, of course, a problem, and yeah, it's certainly a part in northeastern India that causes a lot of landslide, as we see co-seismic landslides. But there has been a lot of studies looking into this a little closer, and what you find is that the effect can depend a lot on the hydrological conditions. So, for instance, if a landslide happens during a dry season, if an earthquake happens during a dry season, you may find that there are not as many landslides as if the earthquake happens during the wet season. So clearly what we've shown today is also applicable actually to these conditions, because you can feed into your models whether the area is wet or dry, and this may tell you whether there will be an earthquake, whether landslides will be triggered during an earthquake or not. But in terms of what measures need to be taken before constructions, I think what I try to emphasize is, or what I try to highlight is, what is being done in a lot of areas where seismicity is a problem. Quite often what you do is you look at seismic site characterization. So you try to estimate what are the seismic properties of the subsurface where you want to build. And based on that, you can estimate amplification factors. So if you get an earthquake and you have very loose soil, for instance, it can be that you're amplifying your earthquake base, and then you get more landslides. So clearly, what's done often is looking at these microseismic zonation and trying to estimate where it's safer or where it's not so safe to build, and then kind of build accordingly.
Okay. Dr. Maneesha, your input?
I think we can move on to the next question because time may be also short. So any one of us can answer, I think.
Okay. Okay, so next one, which was not. This question is from Hari. What parameters do the sensors collect from the site to make the prediction model?
It depends on what is the domain you are working on. The parameters vary with respect to whether you are actually trying to monitor flood, or are you monitoring landslide, or are you monitoring earthquake. In the case of landslide, the different parameters which we look forward is the triggering parameters majorly, that is rainfall, which is for the rainfall induced landslides. The major triggering factor is rainfall. Then at the same time, how the moisture variability which is happening under the subsurface, which is moisture. Then the pore pressure, the pressure which is building inside the pore, so pore pressure sensors, and also to understand the movement characteristics which are happening inside the earth subsurface, we use actually geophones which will capture the vibrations, and also to understand the slope instability, we have strain gauges, inclinometers, and tilt meters to tell us the variations in the slope angles also. And those are the in-situ sensors which we have used.
Okay.
If you want to add something, please feel free to add.
Yeah, no, I think that's very well covered.
Okay, so the next question is from Swapna. In Arunachal Pradesh, it is observed that the local cloudburst, heavy rainfall is causing landslides near a lot of residential areas. So can early warning be used for this kind of situation, for a cloudburst situation?
So early warning on a cloudburst situation is, as of now, you don't have very good forecasting systems for the cloudburst scenario. And because it happens for a very short span, in a very large scale rainfall happens at that point. But at the same time, most of the time we had seen cloudbursts during monsoon periods. So that can be one reason. If you have an antecedent rainfall condition, where you will be able to model those antecedent conditions and then give you a forecast, rather than a cloudburst based forecast for landslides, which will need some more years of research, I would think. I think the Ministry of Earth Science has put in some of the energy into this type of research and deploying a lot of radars all around the country to capture these details. So climatic models have to be built. I know that the National Weather Forecast Medium NCWMRF has already have looked into how they can come up with forecasts for 4 kilometer and 30 kilometer range. I think they are further improving it. So it's a large scale data problem and large scale measurement problem. So it needs little more time to get into the forecasting side of it.
Okay, moving on to the next question. This is from Krishnantini. Do we have any technology or improved technology in order to cease forest fires immediately?
Yeah, I started to answer this question already, because actually here in California we have a lot of wildfires, and it's an interesting question too, because what wildfires do is that they usually change the soil condition because of the burning, it changes basically the condition of the soil. And then if the fire is then followed by heavy rainfall, we get a lot of mudslides. And I mean, at least here, there's an increasing amount of research into wildfires, but I'm not aware of any novel technology that ceases fires immediately. But there's certainly research going on in looking at the causes of wildfires and also what wildfires do to basically to the soil, but also to other things.
Okay. Dr. Maneesha, do you want to say something?
There are existing technologies which they have used with respect to IoT, using different sensors to monitor the temperature, the humidity, the wind direction, the smoke, etc. For those using those sensors, they have tried to have an estimate of imminent forest fires. How much it is successful, I am not aware of it. I know that there are people working on those areas.
Yeah.
Okay. Next question is again from Nirmita. The coastal region in the eastern part of India is highly prone towards floods and related disasters. What can be the pre-catastrophic structures we can install in the region? Also, can we utilize the energy for energy generation? As we can say, it definitely has tremendous energy naturally available.
So in the eastern part, if you see that you have a lot of cyclone attacks, at the same time you also have the flood problem. INCOIS has actually deployed a system to early warn tsunami. There is effort for measuring the tides and based on that informing the tidal activities. With respect to flood, even there are simulation based things. I don't know whether real-time monitoring based aspects are there. Structures, there are different types of structures, especially on the ocean side. They have come up with concrete based specific structures and also with respect to hard rock based structures, but over the years naturally they all go away based on as the ocean's activities go along. So there is always, you have to replenish whatever it is has been taken over by the ocean. So I think these are the limited knowledge I have with respect to the ocean side.
Okay. So the next question is from our very own Dr. Vadvan sir. Can we predict vulnerability of areas with older landslides incidences, reactivation of older debris? Is that possible?
So based on the landslide areas and how much historic data you have, and with the real-time data now, you should be able to estimate the probability of a slope instability.
Also, if you have all this information, I think you can then feed it into numerical models, and yeah, as Dr. Maneesha already said, then you can estimate what the factor of safety of the slope is, and you can also run different scenarios and see how different climatic conditions may actually cause the kind of reinitiation of the failure.
Okay, so we have another question from Sapna. How do we bring awareness to the communities about landslides and landslide indicators or precursors in a changing climate and land use variability? So
Amrita has actually extensively worked with the community, where we have brought out a participatory model where we have groups which has been developed in these different landslide prone areas, who will work with very closely with the research group at Amrita. We also have built-in systems and solutions using crowdsourcing approach, using mobile apps, where they are able to have a communication with us on what are the variabilities they are seeing on the surface or the weather or etc. And we also are working with solutions where we are looking into the social media posts, like whether it is Facebook or Twitter, and see whether we are able to see that any withering condition is coming. This is part of our landslide project, where we have partners from King's College London, Newcastle, BGS, UK Met Office, etc. GSI, etc. So that is one approach, and we have regular interactions with them over the virtually online and also in-person interaction with them, where to build the awareness program and to understand what is their knowledge level, because there are sometimes their knowledge also contribute to the research, because they may know the changes better than us what they are seeing on the surface. So they becomes an informer and also participant and also learner in this whole knowledge process along with us. So we together see, like if you see a change, they will surely let us know, and we will look into it, what does it tell. And if they know that this change means something else, they will say, are you seeing the same change in the sensor? So the community has to be held in hand in the whole local governance, which will help you to bring in the resilience. Now, providing the knowledge and engaging them in this whole process is the prime needed thing for building resilience in the community.
Okay. Thank you, Dr. Maneesha. Moving on, can you please elaborate on the e-resources to study the seismicity using IoT?
E-resources. Yeah, if you know, Seb.
Well, yeah, I'm not entirely sure what you mean by this question, but there are some global seismic stations that you could use to look at the seismicity for a certain area, but other than that, I'm not entirely sure.
Okay. So the next question is from Meda. Will planting more trees help to reduce the impact of landslides as it improves soil resistivity? Yeah.
It depends on the type of trees you are using. There are different trees. Some of the trees which will help us to hold the soil together. There are some of the trees which will actually take the water deep down into the deep down layers, which can actually trigger more faster the landslides. So that you have to really look into what type of tree or the plants you are going to use. Based on that, you have to work. Like, you know, in Kerala, if you see banana plantation, they may go into the terrain structure, and based on that, they will have banana plantations, which will basically trigger the landslides rather than holding the soil for this. So there are different types of things. You have to look into which type we should deploy, and then we can do. There are cases where we can at least improve a little bit.
Okay, and our last question is from one of our own. Someone talking? Okay, our last question is from one of our own Amrita professors from the School of Engineering. This lecture was very useful. If our UG, PG, or PhD students are interested in developing algorithms, would you be able to provide any data sets or share any data sets?
Sure, there are other students, and naturally we can have further discussions and take forward the research.
Okay, those are all the questions we have for today. I would like to thank everybody for joining the webinar today, and like to thank both Dr. Maneesha and Dr. Sebastian. I'd like to remind everybody to please fill out the feedback form. The link has been shared with everyone. And this session has been recorded, and we will try our best to post the link up on YouTube within a week's time.
Seb, thank you so much for being patiently waiting. I know it's very late in US. And
yeah, it's late. That's fine. Well, thanks for inviting me. So yeah, this was nice.
Thank you, everybody. Bye.
Yeah, thank you very much. Yeah, bye-bye.